Hello student, in this lecture we will discuss some more operations of binomial heaps. And in binomial heaps we need one more procedure that is called binomial link. This binomial link procedure is used to combine two bk-1 trees and convert into a bk tree. Let's consider a simple example. Let's say we have a bk-1 tree which is rooted at node y, and there is some one more tree bk-1 tree which is rooted node at z. It makes z the parent of y. It makes z parent of y in a constant time. Now consider this simple procedure, binomial link of y z, and in first step it makes z as a parent of y, and in the child list of z, in the child of z becomes the sibling of y. Okay, and y becomes the child of z, and degree of z increase by 1, degree of z plus 1. Now you consider graphically, you can consider this. We have two bk-1 trees y and z, and with the help of link procedure we combine those two binomial trees into final binomial trees in which y becomes the leftmost child of the z. That means z becomes the parent and y becomes the leftmost child. Okay, now this procedure is going to be used in the union of two binomial link. Now binomial heap union operations consider two binomial heaps h1 and h2 and unite those two binomial heap h1 and h2 into a single binomial heap. After the combining those two binomial heaps, it destroys the representation of h1 and h2, that means previously given binomial heaps. Now in binomial heap procedure we use an auxiliary procedure that is called binomial heap merge procedure. It basically merges the root list of both the binomial heaps h1 and h2 and makes a single root list, and that would be the sorted list based on the monotic degree of the tree available in the both binomial heaps, and that root list would be sorted in monotonically increasing order. So we can say binomial merge procedure works as a simple merge procedure of merge sort. Okay, now look at this. There are two binomial heaps h1 and h2, and our union operations combine these two h1 and h2. Okay, now in h1 we have four binomial trees, 1 2 3 4. h2 contains also h2 4 binomial tree, h1 h2 these four. Okay, now after merging, the simple merge procedure will merge these two binomial heaps root list into a single root list of a final binomial heap, and that root list is sorted based on the degree. As you can see that this is degree 0, this is degree 0, so both are degree 0, then degree consider the 1 2 3 3 4 4. Okay, for example, now after merging these two lists, one problem arises. It may be possible that both binomial heaps have the same degree of binomial tree. Now in the final root list, it may be possible that this binomial heap, this one converted binomial heap which is made after union of two binomial heaps, may contain the more than one trees of the same degree. This is the violation of simple binomial heap property, because as per the definition of binomial heap, there may be at most single binomial trees of the same degree. Okay, तो एक ही डिग्री का बेसिकली क्या, एक ही आपका binomial tree होगा ना binomial heap. Okay, now to resolve these problems we consider three things. or we consider three type of variable. X denotes the node which is being considered at that particular time. Previous X denotes the node which is left on the root list of that particular node X, and next X denotes the next node on the root list of the final binomial heap, and it is on the right side. So for the node X which is being considered, we consider two more nodes, previous X which comes on the left side of X, next of X which comes on the right side of X. Okay. So in this procedure it may be possible that three tree have the same degree for the time being, but eventually it will be solved, and at the final step we will only have the single binary tree of each degree. Okay, it may be possible that some particular binomial tree is available or not. Okay, but the degree of each binomial tree would be unique. Okay, now let's consider an analogy, as we did an analogy in binomial heap previous lectures. Okay, now if we combine two binomial heaps, let's say we have a binomial heap H1, this one, it contains three binomial trees with degree 0. This is B0, this is B1, or this is B2. Now H2 contains B0, B1 and B4. Okay, in H1 we have how many nodes? 4 plus 2 plus 6. So 4 to 6 plus 7 nodes. So 7 can be represented like this in binary. Okay, now in H2 we have 16 plus 2 18 plus 1 19. So 19 can be represented like this. Okay, this is 19. Now if you want to combine or merge or union these two binomial heap, this would be the resultant binomial heap. This contains B1, B3 and B4. Now for the validation purpose we can do a simple analogy. If we do addition of this binary number and this binary number, we would get 11010. Okay, we would get 11010 because this is for H1, this is for H2, and we do a binary addition. 1 plus 1 0 carry 1, 1 plus 1 1 carry 1, 1 1 0 carry 1, 1 0 0 1 and 1 0 1. So this is the resultant. Okay, now this would tell us in the final binomial heap which type of trees would be available. So if we consider this B0, this is B1, this is B2, this is B3, or this is, let's say, B4. Okay, so in the resultant tree B0 would not be available, B1, B3 and B4. That means in the resultant binomial heap there would be only three binomial trees would be available, which are of B1, B2, B1, B3 and B4. So as you can see that in this result, which is came after the union of these two binomial heaps, is B1, B3 and B4. By the help of this analogy, you can verify your result. Now let's discuss how we get this result. Now for the getting of this result of making of union of two binomial heap, we have a simple algorithm, binomial heap union, which accept two binomial heaps h1 and h2 and makes an, after receiving these two binomial heap h1 and h2, in the first line it creates an empty binomial heap in a constant time and then merge the root list. In the second line it merges the root list of h1 and h2 and assign into the new binomial heap. Okay, that means head h point is the new root list. Now after that it frees the object h1 and h2. If head h is equal to nil, it denotes that your given binomial heaps were empty. That means h1 or h2 was not available, those were the nil, in that return h, simple. Otherwise what it does, it use three variables, previous as x and next of x. Initially previous of x is nil and the node pointed by head h is x and sibling of x would be next of x. Now we get into a while loop and this while loop goes from line number 9 to line number 20. Okay, line number 19 to line number 21, and what it does, it make the use of binomial link procedure, which we have already discussed in little bit before. Now while what it does, let's see, check this out. While next x is not nil, okay, it checks, first of all it checks degree of x and degree of next of x. If degree of x and degree of next of x is not equal, that means the two adjacent tree has different degree, or sibling of next of x is not nil, sibling of next of x is not nil, and degree of sibling of next of s is equal to degree of x. This means this particular condition says that three binomial trees have the same degree. Okay, three binomial trees have the same degree. Next that because degree of x is equal to degree of sibling of next of x. Okay, so for x, next of x is on the right side, and for the next of x, right side would be sibling of next of x. So that means three trees have the same degree. So if any one of these conditions holds, we move forward under the root list, and what we do, we previous of x is changed, now it will become x, the current x becomes the previous of x and next of x becomes the x. That means these are the case number 1 and 2. Okay, now in case after case number 1 or case 2, in case after, if you are using case 2, it will eventually converted into case 3 and case 4. Case 3 and case 4 is the else case of if condition. That means degree of x or degree next of x is not equal or equal. Okay, so if we get the two trees which have the same degree, that means if case 1 and case 2 doesn't hold, we will get into this else condition, and here we check key of x and key of next x. This denotes the situation that our two binomial trees have the same degree. Okay, two binomial trees have the same degree. In that case, as per the definition of binomial heap, we cannot maintain two binomial heaps of the same degree. So we will compare the value of x and value of next of x, or we can say key of x and key of next x, and depend on this condition, depend on this comparison, we would use case 3 or case 4. For the case 3, key of x is less than key of next of x. Okay, and x and next of x are the same degree, so we will use the binomial link procedure. And before binomial link procedure, what we do, the next of x, the sibling of next of x becomes the sibling of x, the sibling of next of x becomes the sibling of x, and we will use the binomial link procedure. Next x, what it does, x becomes the parent of next of x. Okay, x becomes the parent of next. Now if this condition doesn't hold, that means key of x is greater than key of next of x. That means we are in case number 4. If the case number 4, we are in case number 4, first of all we will check whether previous of x is available or not. If it is nil, then next of x becomes the next of x will become the head h. Head h will point to the next of x, and previous of x sibling of previous of x become the next of x, and we will use the binomial link procedure in which next of x becomes the parent of the x, and after that x is changed, it becomes the next of x will become the x, and sibling of x become the next of x, and this loop continues unless next of x becomes nil. And after executing of this loop, when the whole root list is processed, it will return the final binomial link. Now let's consider this binomial heap union operations using graphical representation, and then we'll do one example. Okay, now case 1 occurs when degree of x is not equal to degree of next of x. That is when x is the root of a tree, bk tree, and next x is the root of bl tree, and for some l is greater than k. Okay, here we don't link x and next x, so we simply march the pointers one position further down to the list. This is x and this is next of x, and as we have a sorted root list, that means a value of l is greater than k. Okay, okay, in that case we move forward. That means this c next of x become our new x, and this d, which was the sibling of next x, will become the next of x, and b, which was x, will become the previous x. This is previous x, this is x, and this is next of x. Okay, this was the case 1. Now come to the case number 2. Case number 2 occurs when x is the first of the 3 roots of the equal degree. That is, degree of x is equal to degree of x, next of x, and degree of sibling of next of x. That means we have 3 trees which have the same degree. We handle the situation as we did in the case number 1. That means we move forward in the list, and next iteration will finally convert it into case 3 and case 4. Okay, now this is x, this is next of x, this is sibling, and both have the same degree k. Okay, in this situation we move forward. That means this c becomes the x, this b becomes the previous of x, and this d becomes the next of x. Okay, now come to the case 3. In case 3, in case 3 occurs when we have 2 trees which have the same degree. Okay, in that case degree of x is equal to degree of next of x, but it is not equal to degree of sibling of next of x. Okay, so the for case as we can look you can see, this is x, this is next of x, this is sibling of next of x. Both x and next of x has the degree k, and your sibling next of x held the degree l, and l is greater than k. So this is case 3. The for case 3, the value of x should be less than value of x should be less than value of next of x. In that case, because our heap follows the min heap property, and if it is follows the min heap property, that means our b will become the root of the new merged binomial tree, as you can see in this. Okay, both b and c, both trees rooted at b and c have the same degree bk, so we have to merge, because as per the definition we have only single node or single tree. Okay, or in other words we can say that every tree must have the unique degree in binomial heap. So here we use the binomial merge procedure and the binomial links, so binomial link procedure. Okay, and that link x and next of x or b or c, and b becomes the parent and c becomes the leftmost child of this, and eventually degree will get increased by 1. Okay, so this is the case 4. Now case 3. Now come to the case 4. In case 4 all things are as it is as we did in case 3, but there is a minor difference. This time value of next of x, value of next of, that is c, value of c is less than value of b, or in other word we can say the key of x is greater than key of next of x. This is the, otherwise x and next of x the same degree and sibling of next of has the different degree. In this case c will become the parent of next of key of x, c become the parent of b, as you can see here. And after linking of these two binomial tree, degree is eventually incremented by 1. So bk plus 1, we get a new tree in the root list which has a degree k plus 1. Okay, and the root of this tree is c, and this is previous x and this is next of x. Okay, so this is the case 4. Now let's do simple example. We have two binomial heap h1 and h2. Okay, and after the binomial heap merge procedure we merge the root list of those binomial heaps. Okay, so degree 0, yes, this is degree 0, so this is 18, this is degree 1, yes, degree 1, this is degree 1, this is degree 1, this is degree for degree 2, this is for degree 2, and this is for degree 4, and this is for degree 4. That means we merge the whole list based on the degree. And as per the algorithm says, the node which is pointed by head edge is x, and the sibling of x become the next of x. Okay, now we will do our analysis. Now x and next of x both have the same degree, and sibling of next of x has different degree. That means case 1 and case 2 are not applicable. In this case, case 3 and case 4 applicable, and it totally depends on the value of x and next of x. In our case, value of x is less than value of next of x. So other case, key of x is less than key of next of x, and that means case 3 is eligible. If the case 3 is eligible, what we do, 12 x becomes the parent of next of x, or what will happen, we will get a new tree, this tree, after using the link operation. So 12 becomes the root of 18 and the degree is 1, b1. So we get a new tree in the root list. Okay, now this will become next of x. So next of x, sibling of x become the next of x. Now if you can look at this scenario, look at this. Yes, if you look at this, at this particular time we have 3 trees which have the same degree, x, next of x, and sibling of next of x have the same degree, degree 1, 1, 1. That means this is case number 2. The case number 2 because all these 3 trees have the same degree. In this case we will move forward down to the list, and this next of x become our x. After using case 2, so this 7 become our x, because previously it was 12. So when we move forward, this will become x, and 3 will become next of x, and 12 become previous of x. Okay, so we have here now x and next of x both have the same degree, and sibling of next of x, which is this, sibling of next of which is this, has degree 2, but x or next of has degree 1. That means case 3 and case 4 may be applied there. Now it totally depends on the key values of x or next of x. This time value of key of x is greater than key of next x. That means case number 4 would be applicable here. Now if case 4 would be applicable here, what we do, this 7 becomes the leftmost child of this 3. So here it is. By using link procedure, we will link these two binomial trees into this binomial tree with the help of link operation. So this is our pre of x, this is x, this is next of x. Again, x and next of x both have the same degree. Okay, x and next of x have the same degree. Okay, now case 1 and case 2 are not applicable here. Case 3 or case 4 may be applicable, and for the decision of case 3 and case 4, we will do simple comparison. We will compare the value of key of x and value of key of next of x, and in this case key of x is less than key of next of x. That means case 3 would be applicable here. Now 15 will become the leftmost child of this 3. Okay, so after using case 3, we will get this 3 becomes the parent, or 15 becomes the leftmost child. Now this is x. Now sibling of x becomes next of x. Now x and next of x the different degree, because degree of x is 3 and degree of x is 4. So we move forward, and then sibling of next of x would become our next x, and that is not available. That means it is null. So our while loop stops here, because sibling of or next of x would be nil, and this would return the binomial heap. So this is our binomial heap, final binomial heap. Okay, this is our final heap. So I hope you understand the procedure of binomial heap. Now discuss the complexity of binomial union of binomial heap. Okay, so look at this. So complexity of binomial heap is log n, because you can see over here, this is a constant operation, constant time operation. Now merging, this is a simple merging. Let's say h1 contains the n number of element nodes, and h2 contains n number of nodes. The root list of length of root list of h1 is log n1, and root list of heap h2 would be log n2. Now log n1 are the number of elements in the root list, log n2 denotes the number of elements in the root list. When you merge these, the total complexity would be log n1 plus log n2. Okay, now we can do a simple analogy. Log n1 plus 1 log n is always less than log n. So log n, where n denotes the total number of nodes, in the final tree. So in other words, we can say the n1 is equal to n1 plus n2. Okay, so log n1 plus log n2 is definitely less than log n. So we can say that the line number 2 produces the log n complexity. Okay, order of log n. Now again, this is a constant time. This is also constant time complexity. This is constant. Now check this while loop. Now while loop traverses the whole root list, and the length of the whole root list is log n plus 1 log n2, and as we already discussed, it would be less than log n. So this means this while loop execute log n time, at max log n time, any less than equal to log n time. And in this while loop, what we do, we will do simple constant time operations. This is a moving forward to down to the list. That means a constant. Case 1 and case 2, case 3 and case 4 use the binomial link procedure that itself produces the constant time complexity. So within a loop, any cost of execution of this while loop is constant. Now if we find out the how many times this while loop got executed, this is log n, because log n denotes the size of the root list. So complexity of this algorithm is log n. I hope you got to understand this.